Manas is at University of Maryland, Baltimore County, and he's been working on this for quite some time. He calls it knowledge-infused learning. He's also a book coming out, I don't know when, but in the near future in this area. So Manas, go ahead. You have to unmute. Okay.
Okay. Yeah. So I'm sharing my screen now. Uh, okay. Is my screen visible? Uh, 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 okay.
You're
I
good.
I hope I hope my screen is visible.
No, yeah, you're good.
Okay, sounds good to me. Thank you, Ram, for the invitation. And it's been quite some time after I'm coming back to the forum for presentation. And over the past couple of years, I've been focusing pretty much in the intersection of the generative AI and the neurosymbolic integration, which something is driven by my thought that we are heavily driven by data and relatively less on the knowledge part. So what I've been looking into is how we can actually have a generative AI models driven by the neurosymbolic science. So the focus of the talk today is not going to be very much domain specific, but a bit of the example about would be domain specific as well. So the notion that I started with, that we have this huge race of developing data-driven generative AI models, which are getting bigger and bigger. You talk about GPT-5, Claude, and Gemini, and so on and so forth. And we have this de facto strategy of doing fine-tuning of these models for various applications for different tasks. The challenge that we see is that these models are most of the time they get the information that we get are not satisfactory, and we do not have any calculated way of means to figure out how do we nudge them in a better way that they can give us the desired information. So even if we do fine tuning, we end up sort of overfitting these models to the domain and not really get an idea about how they can really work in the more what Louis was talking about, in a more explainable and interpretable manner, right? And the question is that we do not have at this moment, and I'm this is to my best of my knowledge, that we do not have a principled mechanism about what these models know and whether that knowledge remains stable over the time in the distribution shift, in the domain shift, or in the adversarial conditions. Right. So, for example, let's say I have a model that is being available in the mental health space, for instance, which fascinates me a lot. Um, can we have this model working in the cognitive behavioral therapy, right? Can this model do the screening? Can this model be able to do some clinical summarization? So for every different task, we just keep on fine tuning these models for different applications, which make them more data heavy as opposed to knowledge heavy or knowledge driven. That's the major piece, because with the knowledge, you do not really need to memorize things. You do not need to claim things, but rather be more specific in your responses. So what I've figured out that LLMs exhibits the systematic bias towards high frequency designs, and their understanding is pretty much pattern matching as opposed to a genuine understanding over the domain. And I added over there the word genuine clinical understanding because that's where most of my work in the mental health space is being driven, where I've been looking at how these generative AI models can be brought to, and we can we have a feasible solution from these generative AI models in the mental health space, where we are already going away from that point that these models are not able to do a real world deployment, for instance. So this thing is not something that I am the only one who is looking at, but there are some neuroscience researchers who have taken a deep dive into to understand how these neuron specific feedbacks in LLMs work, and are they connected to the brain. So think of this in a scenario where we are neuroscience researchers are trying to understand what is happening inside the LLMs. What are the connections What are the concepts being represented? Are those concepts related to the task, or they are irrelevant to the task? So so far there is no plausible answer to this question, but this is where I see a huge promise from the neurosymbolic AI community, where we can understand a lot of these informations through structured knowledge graphs or different forms of knowledge that we are having at our disposal. The question is, what are the methods that we can devise to do that precisely? So that's going to be the focus that I want to drive in this talk, right? So, uh, keeping this fact straight, uh, I'm not a huge proponent of scaling. We really do not want large and large models to do our task. We really want more interpretable and transparent models. Retrieval augmented generation that came into the picture did not really solve the purpose of black boxness of these models, and then people started uh, looking at probing as one of the cases in the LLMs to figure out what are the different reasons that these models do. For instance, you can think of probing as sort of putting a lens over your LLMs and see what are the connections and what are the causations and correlations happening inside the LLMs. Now, when we look at these designs, right, the problem arises is what I call it as an impossible triangle. And we are getting stuck into that with the current generative AI model strategies. First of all, we are heavily driven by scale. We are losing interpretability. Even if we are going over the interpretability, which the Google DeepMind came up with called the Neuronpedia, to allow you to look inside the LLMs, we are looking at interpretability, but we do not have a definite way of doing grounding, or we do not have a definite way of um, basing these models over a particular structured knowledge. So things of them, much of those information are probabilistic in specific. Even if we do grounding using retrieval augmented generation, it's not scalable because retrieval augmented generation, think of this as a traditional IO operation, input output operation, which is taking a lot of time. And no matter what happens, RAG is sort of the slowest piece of design. And if you want to make them fast, um, either you have to sacrifice in your structured data, or you have to sacrifice in your model's performances. So there is always a trade-off that we are getting stuck in the RAG scenario as well. So uh, when we talked about this recent interest that rose in the LLM space called the probing, we are trying to understand what these models are actually looking at, right? What are the concepts that it is looking at, and are those concepts important? Are they relevant to the task or not? Right. So we become more towards correlations as opposed to causations, and causations means like, are the two concepts connected just because they are meant to be connected because in the data, or are they connected because there is some sort of an external knowledge that is guiding them, right? And is that knowledge correct? And we can actually cross check them through some kind of a visual means. But when we look at this probing mechanism that have been developed in the recent couple of months, we see that they are very much data driven again. So we need to think of this, that if I want to understand if my model is doing a good job in truthfulness, which is the Google's flagship data set of truthful QA or truthful question answering, I am using another set of data to understand whether the truthfulness is actually truthful or it is a fabricated piece of information. So what we do is we create adversarial data set, right? And we are not testing them against knowledge. We are testing against another set of a data set, which we construct as an adversarial set. Now, now the question arises, how can I know that my adversarial set is complete, is correct, and is plausible for the probing task, right? So there are some lot of these questions that arises in the way we define where we define how do I look inside this network and able to make sense that, oh, these connections are correct, these connections are incorrect, and things of that nature. So this is where I see that neurosymbolic AI fits perfectly to answer the questions that neuroscience researchers have. even the questions that raised by broader uh, AI community per se as well, where we try to examine ways in which we can incorporate uh, domain-specific knowledge, lexical knowledge, common sense, and constraint-based knowledge that exist in various applications to guide the model. Let's say, when I say guide the model, I'm trying to say that I'm not saying to fine tune the model, but here's a base model that pretty much do a good job in generating the text in a manner. I want to steer that model. I want to move that model in the direction of my knowledge. And that's the thing that I would really want to do. And now in that process, I want to also chop off some unnecessary connections. I want to remove some of the layers that are not needed at all. That's a like this work also, this sentence that I just spoke, that we want to cut some of the layers, is nicely explained by Max Tegmark in his recent paper on stitching networks, where he say that we do not really need this big network to solve problems in the real world space. So this is where my intention to do a more knowledge infused design for these generative AI models fall into, and giving my interest into retrieval augmented generation and so on and so forth. I have seen that these strategies, these frameworks are not really ready for the prime time in sensitive applications. So this actually puts me into a burning questions in my head, and I want to just throw it out and keep the and in front of the community and see what interest arises in the space. So the first thing that I arise, well, the first question that I think of is, can we detect and localize these knowledge gaps? Right? LLMs have knowledge gaps. When I say knowledge gaps, I will talk about. I'll show you a hierarchy, and I'll also give you a more dense hierarchy of what these knowledge gaps are as down the top. But I really don't know what about their representation, how that representation is connected to the ground truth or the knowledge structures. Uh, do they access their knowledge when they are needed, or they just try to cook up something to give you an information? So we really need to detect and localize these knowledge gaps. The second is, can I take these internal model computations, which I call the computation graph, very famous term, came out from the TensorFlow literature, into more symbolic abstractions where we can understand and localize these graphs uh, into specific circuits, right? And in this process, when I'm localizing these gaps and understanding these neural circuits, uh, can I understand them through the knowledge graph per se? And after we have done all of these things, the question is that now I understood. Let's take an example, like I'm hypothesizing right now that let's say we understood which area or which segment of my neural network or my LLM is really the culprit for the problem. Can I do some targeted modifications over there rather than structuring the entire network altogether? And we are not thinking of doing it randomly. We are not thinking of doing it through data. We are really thinking of doing it through structured knowledge to see how can I resolve those gaps and make the model more adaptive to the domain that we are really wanted to work on. Okay. Yeah. So this is my thought of understanding of what these knowledge gaps are, and what are the confounders in the LLM. So I want to just make this thing very clear in the separation of where we are in the LLM space. So when I say knowledge gaps, right, one of the things that really pops my head is the representation failures, right? Concepts are absent, right? Or the concepts that are present in the LLMs are not really the ones that we think of are useful for answering the question. But we get to know them only from the performance. We don't know them whether they are being in the vocabulary or when are they being used and things of the nature. Access failure means the model encodes, let's say, some information, but they are not really contextualized in the query that is being given to the model. The last part is more of most of an expression failure. Like even after I did the fine tuning and heavy lifting, and somehow I get to the point where the expression the model is making is retrieved, right? The application of those concepts are again a question of doubt. And that's where you put it into a supervised fine tuning, and again you become more data driven as opposed to be more knowledge driven per se. Now, these are the gaps, but these are the gaps because of confounders that we see in the LLMs. The first one is the memorization part, right? The second one is what I call as a polysemantic interference, because you want, let's say you think of, let's say I want to have a smaller models for applications, but then every single neuron will now become more polysemantic, right? And you don't know what that polysemantic going to mean, are going to be. And there are some artifacts that in which that are there in the data sets that actually are the constituent factors for increasing the memorization and polysemantic interference, right? And then at the end of the day, what we have is a model that do some shortcut reasoning, right? So this shortcut reasoning is what I call as a local source contribution, right? So let's just talk about this, what LSC means in the LLM space. So what does LSE is? So LSE is a behavior that I understood from the LLMs, be internals, which is which part of the input or the retrieved knowledge actually influence, right? I'm being very modest with the LLMs right this moment, but it's not really a retrieved knowledge, it's really a retrieved concept. Uh, that actually influence the model's final answer, right? So high LSC means all the relevant tokens have been identified, uh, correct reasonings are happening. High LSC also means that there is also misleading or local phrases have been identified, which can also be caused to high hallucinations and myth propagations. So both of these are like LSC is something that also can give you a right answer. LSC also can also give you a wrong answer as well. So this is a common trend in which how the LLMs trying to understand this behavior, right? So we found that this scenario is very much correlative to the attention that we really talk about, and we see that even if the model knows the answer lies in a multiple choice question answering setup, for instance, right, where the answer is there in one of those points, still the model makes a guess on those questions, right? And if you see over here, the LSE contribution score for the for a model, and these are all of these results are on the Llama and the Gemma. Both of them failed in the scenario. We see that these models have been in a tendency where they really focus on what is happening in the nearby neurons and not really capturing the broader picture of what the question is, right? So think of so that's where I see a lot of the confusion arising inside the model, and you can very much localize them. You can detect, so once you detect them, you can always localize them in certain layers inside the LLMs as well. So the idea was that to make sure that these LSC is being driven by knowledge as opposed to be driven by the data, which is the current mode of operations in various LLMs going forward. Right. So this LSC also allows you to make sure that your LLMs are aligned to the domain specific resources. So this is a broader concept that is, think of this as a way that LSC is both a good thing as well as a bad thing. But if you really want to make it a good thing, the only way you can do it is by adding some sort of a knowledge into certain layers of the LLMs, right? So this can really gives you the behavioral interpretability, but I cannot really help in sort of elevating the gaps inside the model. LSE does not give that capability to me. I cannot elevate the problems. I can only interpret the behavior of the LLM, locate the things. That's all I can do with the local source contribution design. Right. And we saw that in Truthful QA and in the HelloEval scenarios, which are the prominent data sets to really see the truthfulness structure of these LLMs. And we see that when we see their papers on the QA study that happened a couple of years back, we see that the models have like 80% performance on truthfulness. But the moment we ask the model through LSC to pay attention to some of the let's say entities numbers and exceptions and so on and so forth, like different symbolic triggers that we really care the model to pay attention to, we see that these models tends to have a higher hallucination rate, right? So now this creates a very nice in my opinion discrepancy between what is being tested in the truthfulness or truthful QA versus what the models are actually learned. right? So when we look at these modifiers, named entities, numbers, negations, and exceptions, we see that these properties are never caught in making the decisions, right? So hallucination on these are immensely high, despite the overall performance of the model on the truthful QA is there. So there is some sort of shortcut reasoning happening in the model that is diagnosable through symbolic structures, but now we really need to look at how do we correct them. We have a way of looking at identifying the segments in the model where things are going off, and we know that the hallucination is still high. Now we really need to look at how we can correct them. And we have seen this behavior in logical reasoning problems. We have seen it in the therapy problems where we have tested these LLMs that were released to truthful QA. And the one of the interesting factor that I really want to pay attention to over here is that on the right side of the table, right? The right side of the table, which is of the cognitive behavioral therapy, one of the clinicians actually told me that the model is heavily biased towards validation and reflection. It's not really doing questioning, it's not really doing this restructuring and so on and so forth. So this tells me that the way we are doing the fine tuning is just letting the model adapt to one soft space, comfortable space, which we in machine learning we used to call it as a VC, Vanosky VC dimensions, where the model is comfortable in making the predictions. But it really didn't tell us that how we can move the model to have equal weightage for other segments in the problem space. So these are some of the problems, strategy that we found that, okay, we have localized the regions in the model that are really the culprit for these behaviors. Now we really want to see how we can steer them or change their behavior over the time, right? So I want to skip this part because some of the things have already discussed in the part. So this is a bigger picture of the confounders and the knowledge gaps that I just lay down a couple of slides back, where I'm not talking about now a knowledge gaps, which is entity resolutions, procedural knowledge, domain explanations. These are some of the gaps that I see in the LLMs. Negation, context, semantic relationships, directions. For each of these things, think of this that we can't have data sets being constructed for each of these gaps and confounders, right? To be a huge uh, arena for data-driven AI as opposed to knowledge-driven AI, which we really want to go for neurosymbolic style. And most of this information are very much solvable through the neurosymbolic integration inside the generative AI structure. Okay, so what perspective that I bring in from symbolic is that this allows us to have structured knowledge being a core piece to be driving the LLMs. That's the first point. Is that I really want to look at more about constraint aware generation in these models, which can be driven by knowledge graphs. The interpretability angle of these LLMs can also get benefited from the knowledge graph. And what you really end up doing is that you're sort of resolving the knowledge gaps inside the LLM without adding data. That's the prime goal of going with the neurosymbolic structures. So going further, in when I say quantifying the knowledge gaps, I really want to talk about in the interest of time, I'll only cover one part, which is called the knowledge constraint probing for gap detection. And the second one is more about looking at making the RAG or the retrievers in more grounded through knowledge graph integration. So the first thing that I wanted to present in the session today is about the KG constraint probing, which is one of the way which we found to be very interesting in at least understanding that the model's concepts and features are the ones that align or that are present in the knowledge graph. So what we did was we praised the LLMs and we read its internal signals first. We take a particular layer, we extract all the activations from that layer, and we want to understand what those concepts in those activations represent. Second is we have trained a sparse autoencoder over a knowledge graph, which allow us to give some representation of the concepts. we will see those concept representations that are there from the knowledge graph are mapped to the activations or to the concept and the feature space inside the LLMs. Third was to look at those information and see the discrepancies between the two. And from those discrepancies, we really want to update the LLMs or maybe like classify which are the weak entities, weak relationships, or absent concepts and try to update the LLMs in that space. So this sort of gives a nice strategy for steering these models using knowledge graphs, leveraging autoencoders, the common mechanism of representation learning in neural networks, and also bringing a very nice flavor of neural space and the semantic space together in the probing mechanisms. We also examined that there is a very nice way of doing KG paths or knowledge graph path retrievals in the RAG that allows me to do two things. One is I can know which document was selected. I know why that document was selected and how the document was being used by the model in the decision making process. So the step that we followed is the following. We start with an uncertain knowledge graph. We learn which edges of that knowledge graph are relevant based on the query and which of them are noisy. We rank the documents of how well those queries are being so we rank the document based on the queries and the path being followed. So think of this as the top. So I start with a user query, QE, and gradually go over the graph, identified which of the entities are noisy, and gradually, over the period of time, I'm having a path of all the entities being traversed through this mechanism of optimizing the document retrieval and optimizing the knowledge graph as well, right? And once you're done with this, it's pretty easy to have this traverse knowledge graph, to do a traversal over the knowledge graph using a breadth first search, retrieve the documents given based on the uh, uh, knowledge graph. And then lastly is to use that information, to use that retrieve documents to for your answers. Now, here is a thing that I want to really emphasize. Your answers are not driven only by the document that you have retrieved. It also depends upon the enriched query that you got from the knowledge graph, as well as the KG path that you have identified from the graph as well. So this allows you to have a nice inference over the standard retrieval augmented generation mechanism. So this does not really give me an insight of the LLMs, but it really makes my retriever, at least my retriever, neurosymbolic compared to my generation. My generation is still the same, but my retriever is now becoming more neurosymbolic space with my KG integration. We tried it over like 6, 7, 8 data sets, and we consistently outperformed 33 billion parameter models with just 3 billion parameter model. On the KG path RAG and the Prono RAG that we had, both of them are just 3 billion parameters altogether, even with the RAG, and they did far better than or relatively better than a 33 billion parameter models in per se. So this, I want to switch some directions over here and want to really, in the interest of time, just jump to the main angle of mechanistic interpretability in this space where I'm talking about saying that we really want to have three key instruments for really understanding the internals of the LLMs. And now with the RAG in place, we have two LLMs in this picture. One is an LLM in the retriever, and other is an LLM in the generator side. So we really want to have first is a knowledge graph sparse autoencoder that allow us to modulate the internal representations of the model, at least study them. The second is more about interpretability of those representations and steering them, where much of the topics that what Lewis talked about are doing deductive, inductive, and abductive reasoning circuits are very much present inside the LLM, but they are not identified. They're not being used by LLM per se, right? And the last part is more about sparsification or sparsifying this entire network with the information that really matters to the so to really condense your model. Okay, so one thing that we really are proud of in terms of the neurosymbolic space was this parsification of this gigantic big model that we started with, which is around coming up with some around 13,832 edges. Right now, we are working with it on only with the 7,000 edges of this network, but we are also sparsifying it further. So what we found was that when we keep on sparsifying this network with the knowledge graph, we are still faithful with like 91.5% with only 70% of the edges preserved. And we found this to be far better than LoRa and other mechanisms which are data driven compared to a knowledge graph driven specification of this model. So that means that if I have access to the internals of the model, I can chop some of the unnecessary circuits. I can identify more inductive, deductive, and abductive circuits and keep them and preserve them for my decision making rather than having it more data driven, right? So this I want to summarize my conversation throughout that we talked about to 4 or 5 points that really drives the semantic mechanistic interpretability space, which is where the neurosymbolic angle, in my opinion, has a huge role to play. First is to have the detection of the knowledge gaps. Second is to localize the deductive, inductive, and abductive reasoning circuits. Very relevant to what Lewis just talked about in the previous talk. We can actually distinguish memorization from grounding the knowledge. We really don't want our models to memorize things. And then we can even targetedly steer these models without fully retraining them altogether. And at the end, once we have these models, we can now have an auditable way of explanations as opposed to make it more hunch-based scenarios. So I'm just putting thoughts of these three constituent ideas together, which is neural, symbolic, and the causal, put together into the semantic interpretability space for really having a deployable LLMs for real world applications. So this is where I want to stop and see if there are any questions. And going for my road ahead, some of the things I really wanted to add, and this I added after having so listening to what Lewis was mentioning. So we released this counter logic dataset that's through IJCNN conference, which allows us to test the internals of the LLMs on the logical reasoning part. We just completed a dataset on theory of computation of the finite state machines. Some of the things that we tried out with the clean closures and things. We released the ReDFA datasets, which is under review at TMLR. We looked at redefining the LLMs through rationals. We are also interested in looking at this memory-driven agents as well. And lastly, I already talked about the cognitive behavioral therapy per se, where we saw the bottleneck in the current LLM strategies. So all of this driven research are a part of my previous efforts. Started in 2024, where we talked about CREST, and these are all in sort of a nice causal research going into neurosymbolic AI space. With this, I thank you all for any for giving me the time, and I look forward to any questions. And this is a very high level figure that I want to bring in, where I see a lot of papers talking about neurosymbolic. They're selling methods by the name neurosymbolic, but they're not really neurosymbolic per se. So this is just my small hierarchy about those methods as well. So chain of thoughts have been talked about as neurosymbolic, which I don't really think it's neurosymbolic. Tree of thoughts, self-consistency, DPO, RLAIF, instruction fine-tuning, they're not really neurosymbolic per se because they're not really having a bidirectional neural symbolic integration altogether.